In this video, we will attempt to solve for the volume underneath the bridge at Lawrence Hills Pond. However, before we do this, we first need to learn how to approximate area and volume using methods such as LRAM, RRAM, and the trapezoid rule, and then how to find exact values using integrals. However, when we do get to this portion, we first need to solve for the area of one cross-section, as just shown in the movie, and then we will take the antiderivative of that over the integral of the width of the bridge, and that will give us the entire volume. Now let's jump straight into LRAM, RRAM, and the trapezoid rule. Here we have a graph of y equals x squared, and we want to find the area under this curve from 0 to, let's call it 4. And we currently don't understand or know how to find the exact amount, so we can approximate using methods known as LRAM, RRAM, and MRAM. So LRAM is when you take the leftmost endpoint on the curve and find a rectangle with a certain length change in x, or delta x. So if we make, let's say, 2 equal subdivisions right now, so 0 to 2 and 2 to 4, we can take the leftmost point at each of the subdivisions and find the area at those 2 points of those rectangles. So we have one rectangle here, and this rectangle will amount to 0. We have change in x, which is 2, times the height of this rectangle, which is going to be y is equal to 2 squared, which is equal to 4. We know that the left-hand approximation of this curve is going to be 8 units squared. Now we're going to take a right-hand approximation, which is known as RRAM. And similar to LRAM, instead of using the leftmost point on the curve, we're going to take the rightmost point. So here that would be at x equals 2 and at x equals 4. Just like that. And then you're going to calculate the area of those 2 rectangles. So it would be the height times the change in x, which is going to be 2. So you're going to have 2 times the height here, which is 4, plus 2 times the height of y equals 4 squared, which is equal to 16. And you can also simplify that to be 2 times 4 plus 16, which is going to be equal to 40.
Now, both these approximations, LRAM and RRAM, are either less or more than the actual area under the curve between 0 and 4. And so to get a more accurate approximation of the area, you're going to divide LRAM and RRAM by 2, which is also known as the trapezoidal rule. In this particular equation, LRAM is an under approximation of the area and RRAM is an over approximation of the area, and so dividing them by 2 will give you a more accurate representation of the area, even though it's not necessarily the exact area, which we'll learn later.
So as Kedzie explained, that is how you calculate the trapezoidal rule, LRAM plus RRAM divided by 2. But instead of calculating out both of them and then dividing by 2, there's an easier way to do it. So you take the change in x divided by 2 of the first y value plus 2 times the second, all the way up to the second to last one, and you multiply each one by 2, and then you take the last y value and it's just 1, and that actually is an average of LRAM and RRAM. So for example, in this case, we have trapezoid is equal to change in x, which is 2, divided by 2, because it's an average, of the first y value, which is going to be right here, 0, plus 2 times y1, which is 2, or sorry, which is 4, because it's y squared, plus 1 times the last one, which is going to be 16. and then that becomes 24.
Okay, now that we've learned about LRIM, RRIM, and the trapezoidal rule, which are only approximate ways to find area, we're going to use integrals to find the definite area of the shaded region. So in this particular problem, you're given the equations y equals the square root of x and y equals 2, and the shaded region is going to be bounded by those two functions, and that's the shaded region here. And so in order to find the intersection point, which you need for the upper and lower limits of integration, you're going to set the square root of x equal to 2. So x is going to be equal to 4 because the square root of 4 is 2, like that. So that's going to be 4. And so now that you have the upper and lower limits of integration, you're going to find the area of the shaded region. Because you're given these two functions, 2 is on the top, and so you're going to have 2 minus the square root of x. So you're going to subtract this function from this function, and since it's in terms of x, you're going to have dx. Now we're going to take the antiderivative of 2 minus the square root of x, evaluated at 0 and 4. So square root of x can be more easily written as x to the 1/2. So the antiderivative of 2 minus the square root of x is going to be 2x minus 2/3 x to the 3/2. And that's going to be evaluated at 4 and 0, and you can do that with a calculator. Now that we've used integrals to find the definite area of the shaded region, we're going to use integrals to find the volume. And so in order to make this a volume, we're going to rotate this shape around the y-axis. This is what it's going to look from the front, but it's really a 3D shape. And because we rotated it around the y-axis, the integral is now going to be in terms of y. So it's going to go from 0 to 2. We know this point is 2 because the shaded region is bounded by y equals 2. And so even though that the shape looks like a cone, I like to think of it as a bunch of circles stacked on top of each other. And so we're going to use the equation pi r squared in our integral because that's the area of a circle. And so we have pi r, which is the square root of x squared. But since this is in terms of y, we need to replace the square root of x with y. So we take our equation y equals the square root of x, and you solve for y. So y squared equals x. So instead of plugging this into our integral, we're going to plug pi y squared into our integral. So it's going to be pi y squared dy. Now we're going to find the antiderivative of pi y to the 4th, evaluated at 0 and 2. So you're going to just repeat pi, and that's going to be y to the 4th, essentially, evaluated at 0 and 2, dy. And that's going to be pi 1/5 y to the 5th, evaluated at 2 and 0, and you can solve that on your calculator.
So now that we just calculated the volume when rotating this area around the y-axis, we're now going to calculate it around the x-axis. And to do this, we need to use a method called washers. So when we rotate this around the x-axis, we get a shape like this. And basically, when you rotate that, there are going to be two circles, and you need to subtract the bigger one from the smaller one. So the equation for your area is going to be pi times big R squared minus little r squared, where y equals 2 is going to be your big R, and y equals the square root of x is going to be your little r, because this is higher up than y equals the square root of x. So when you go ahead and plug in your values of x, you get area is equal to pi times 2 squared minus the square root of x squared. And you can simplify that to be pi times 4 minus x. Now we're going to find the volume by taking the integral from 0 to 4 of the area equation that we just got below, over there. So we're going to plug that in, and we're going to get volume equals pi times the integral from 0 to 4 of 4 minus x. Then we can go ahead and antiderive this. So volume is equal to pi times 4x minus 1/2 x squared over the integral 4 to 0. And you can do this on the calculator. Now that we know how to use integrals to solve for volume and area, we're going to solve for the volume under the bridge of the pond. So our first measurement for the bridge is going to be solving for the diameter so we can then find the radius. We are going to assume that the area under the bridge is a semicircle even though it appears as just an arc. But we're going to find
232 inches.
232 inches. Now we are taking a measurement of the width of the bridge, which is
inches.
How long?
48.
48, and we're going to take the integral from 0 to 48 of this bridge when we find the volume. Here we have the diameter, radius, and width. Now we can solve for area. Using the equation 1/2 pi r squared, we solve for area. To find volume, we now take the integral from 0 to 48 of the area. After using the fundamental theorem of calculus to evaluate the integral from 0 to 48, we arrived at an answer of 1.015 times 10 to the 6th inches cubed. That is the volume under the bridge.